Last section we discussed optimization problems. Those are problems where instead of just solving for a value, we instead are trying to maximize or minimize some particular quantity. Most of our examples were using more geometrical ideas like areas or volumes, but in this section we're instead going to do examples using things in business and economics. Before we actually get into the problems, let's remind ourselves of some of the variables and formulas that we've used when we actually do these business type problems. So most of the time we have as our independent variable x, which will stand for a number of units. This could be units produced or units sold, anything of that kind of the sort. We'll generally have little p stand for price if we're selling the units. A lot of times we'll treat price as a function of the number of units. That is what we call a demand function. So demand function is something like p equals some function of x. This might feel a little bit backwards because you would think that x, the number of units that you actually sell, would depend on the price, but for some reason in economics, and I'm not an economist, I'm a mathematician, of course, so I can't really explain all the stuff here, but for some reason we're going to be treating price as a function of demand instead. Usually it's nice enough that we can solve for either x or p depending on the situation, so it's fine to put it in this way. If you want to think of it as x depending on p, go ahead. We just solve for p in our formula. Then we have three other quantities. We have the cost, which we denote by a big C. We have revenue, which is a big R. And profit, which is a big P. Unfortunately, I'll have to say big P and little p for price and profit. Now, based off of these, we have some very specific formulas that always hold true. For instance, the profit is always the difference between the revenue and the cost. And revenue, if we already have the price and the number of units sold, is always going to be the product of those two things. So revenue here being just the raw amount of money that you get from selling those particular units at that particular price. We are going to use these formulas and ideas in setting up all of our functions that we want to optimize. I'm going to start with problem 16. So we're just going to kind of run through some problems and see how this all works. But it's all going to be based off of the formulas that we just had. In problem 16, it says a commodity has a demand function modeled by, and it just gives us a formula for it. We don't have to come up with it ourselves. P is equal to 100 minus 0.5 times x. And a total cost function modeled by, so they give us the cost function as well. C equals 50x plus 37.5, where x is the number of units. Then they have two questions. A, what price yields a maximum profit? So they're wanting us to maximize the profit. And B, when profit is maximized, what is the average cost per unit? We'll come back to that in a moment. But first of all, we want to maximize the profit. Even though they give us a formula for cost, that's not what we're trying to maximize or minimize. So we're going to have to find a function, a formula for the profit in terms of x. So we'll start with P, which of course the only thing we have to know about P right now is the difference between R and C. Of course, we already have what C is, but we need to find out what R is. So R, we're going to use our other formula, x times P. But since we already have our formula for P, we can go ahead and just replace the P in here with that particular expression. So we can have this x times the formula for P. So it'll actually help to go ahead and expand this out. I'm going to distribute that x. So we'll have 100x minus 0.5 times x squared. And now I can go ahead and put this formula and the formula for my cost into my formula for profit. So P, capital P, is equal to this formula here. It's 100x minus 0.5x squared minus the formula for C, which is 50x plus 37.5. Now I'm putting parentheses here to emphasize that this negative, this subtraction between R and C, does need to be distributed. When I go ahead and distribute that and combine like terms, I notice here I have a 100x and I'll have a minus 50x. They'll combine to be a positive 50x. We still have the minus 0.5x squared, and we have this last term where the negative does have to distribute to give us a negative 37.5. This is our formula for profit. If we sell X number of units, we will have a profit of this amount. Now, at this stage in an optimization problem, we actually do want to find the feasible domain for our function. What are the limiting factors for X? How far can we go with X? Now, the wording of this problem doesn't really give us a lot of info on what the commodity actually is or any limiting factors in the actual word problem. So we're going to have to fall back on just limits on what these concepts can mean. Specifically here, it doesn't make any sense to have a negative number of units. So we're going to make sure that X is at least 0. X is going to be greater than or equal to 0. But it also doesn't make sense to have a negative price. So we're going to say that P is greater than or equal to 0 and use the formula for P to actually give us the limit on X. Basically, this is just saying that 100 minus 0.5x has to be positive, or be non-negative, I should say. If I go ahead and solve this, we can go ahead and say that 0.5x is less than or equal to 100, or that x is less than or equal to 200. So our feasible domain our x can go from 0 to 200. So we have a function that we're wanting to maximize over a closed interval. That's probably the best situation that we can have, especially with it being just a quadratic here. We maximize it by looking for critical points. So we're going to differentiate this function. So since we are doing it in terms of differential with respect to x, I'll go ahead and write it as dp dx. That's the way the book has been writing this marginal profit. That's what it refers to it as in an economics perspective. So I'm just going to keep it in that particular fashion. But all we're doing is taking the derivative like we were doing before. Derivative of 50x is going to just be 50. Derivative of 0.5 times x squared, well, the x squared becomes a 2x. 0.5 times 2 is actually just 1. So we get a minus x. Of course, the negative 37.5 goes away. Of course, the derivative here is a linear function. It always exists. We don't have to worry about about the derivative not existing. All we have to worry about is when this equals 0. And hopefully it's pretty easy to see that it only equals 0 when x is 50. So we have one critical point at x equals 50. We have two endpoints. I'm going to turn this into a table. I'll put in values of x. That can be 50 or the endpoints of 0 and 200. And I want to know what the profit is at those points. So I'm essentially going to take these numbers and I'm going to plug them into my formula. When x equals 0, the first two terms go away. We're left with a negative 37.5. Basically, we have this fixed cost of 37.5, and so when we don't sell anything, then we still have that fixed cost, and we end up losing money. For 50, and again, I'm just going to use a calculator here. That's the easy way to do it. So plugging 50 into my formula, I get 1,212.5. I guess I can go ahead and put the 50 on the end of that. Since these are going to be in dollars, or I assume they're in dollars. It doesn't actually say what the units of money are here, but let's assume they're in dollars. For 200, if we plug 200 into our formula, we get a negative 10,037.5. So we definitely don't want to sell 200 of them, or else we're making a huge deficit. When we're maximizing our profit, we definitely are going to be having it here at 50, x equals 50. So we can just go ahead and say we can say a maximum profit of $1,212.50 when 50 units are sold. However, the question does ask what price yields a maximum profit. So we do need to know what the price corresponding to 50 units actually is. Now, of course, we have a formula for that. Our price depends on the demand, or vice versa, by this particular formula. All we need to do is take the 50 and plug it in here. So the price is 100 minus 0.5 times 50, which means we have a price of $75. So when we sell them for $75, we end up selling 50 units, and we have a maximum profit. For part B, they're asking when the profit is maximized, what is the average cost per unit? Now, this is a slightly different thing. The book actually defines the average cost, or the average cost function. So we had C before for cost. We're going to put a bar over that C to denote the average cost. And that's going to be the cost divided by the number of units that are actually sold or produced, or however we're talking about it. This is basically saying the total cost per however many units are in question. In our particular case here, so we have how many units there are. We have 50, corresponding to that maximum profit. But we do need to actually know what cost we're actually dealing with in this case. So cost was 50x plus 37.5. Of course, x here was 50. Go ahead and work that out. We get, of course, using a calculator here, get 2,537.5, which means that our average cost is that value divided by the 50 units that we actually sold. And that comes out to 50.75. Now, the units here are whatever units of money that we have, which is, I'm assuming here is going to be dollars per unit. So it costs us $50.75 per unit that we actually sold. Moving on to another problem, we're going to look at problem 22. In problem 22, we have a small theater has a seating capacity of 2,000. When the ticket price is $20, attendance is 1,500. After a price decrease of $2, however, the attendance increased to 1,700. Assuming that the demand function is linear, what ticket price will maximize the revenue? So in this problem, they didn't really actually give us any formulas to start. We didn't have anything to write down right away. We're going to have to come up with all of our formulas by ourselves. However, they are just looking to maximize revenue. We don't have to worry about any costs here. So first of all, revenue has a formula. R equals X times P. They didn't give us P in this case. We're going to have to find out what that demand formula is. They do tell us that they want to assume that the demand function is linear. They want us to basically say that P is mx plus b for some values of m and b. And they give us two pieces of information. When P is $20, they said that we had an attendance of 1,500. when P was $18 to less than $20, demand was instead 1,700 tickets. These two pieces of information are going to give us information about a line, essentially. We're going to go ahead and calculate our slope. Keep in mind here, because of the form that we have here, x is playing the role of x in our normal setup, and p is playing the role of y. So we have a difference in p's over a difference in x's. Our p's is 20 minus 18, and our x's, making sure we keep the same order, we have 1,500 minus 1,700. In other words, on top we have 2, on bottom we have negative 200, and so overall this is a negative 1 over 100. We go ahead and use this m, and then one of our points, I'm just going to go ahead and pick the 20 and 1,500, and I'm going to solve for b. So 20 needs to equal this negative 1 over 100 times the x of 1,500 plus b. Or in other words, b is going to equal 20 plus 1,500 over 100 is just 15, which is 35. So that means p is equal to, well, let's write it down. P is equal to negative 1 over 100 times x plus 35. I'm going to put the 35 in front, though. P is 35 minus x over 100. That's how I'd like to write it. And therefore, when we put that into our formula for r, and remember, we just go ahead and distribute that x so we don't have to use the product rule. So each of these is going to be multiplied by x. We have 35x minus x squared over 100. That's our formula for revenue, and that's the function that we want to maximize. Now, we do need to determine what is our feasible domain. And this time, we actually do have some information about the situation. Specifically, they tell us that the theater has a seating capacity of 2,000. So we cannot sell more tickets than that. On the low end, of course, we can always go down to having 0 tickets sold. So they don't give us any information that says we at least sell X number of tickets. No, we're allowed to go down to 0. So we can have 0 tickets, but we can't go over 2,000 tickets. That is our feasible domain for this problem. So, similar problem than what we already had for a lot of our problems so far. We differentiate r. It's just a polynomial, so that it's not too hard to do that. We get 35 minus, well, the 2x. I'm going to cancel the 2 with part of the 100 and just have an x over 50. Of course, this is a polynomial, so linear function, so it always exists. All we need to determine is when this equals 0, which is going to happen when x is equal to 50 times 35, which is 1,750. If we go ahead and make a table using this value for x and our endpoints, go ahead and put x and r, put in our endpoints of 0 and 2,000, and our critical point of 1,750. Well, in this particular case, it's pretty easy to figure out what happens at 0. When x equals 0, we're not selling any tickets. We're going to have a revenue of 0. Of course, we can find that just by plugging into our formula as well. Plugging 1,750 and 2,000 to our formula as well, and go ahead and just using a calculator for this. For 1,750, I get 30,625. For 2,000, I get 30,000 flat. And so, which one of these is the highest one? Well, it's obviously here at 1,750. We have a maximum revenue of 30,625. This time they actually did tell us that we're working in dollars. That's our maximum revenue when we sell 1,750 tickets. Of course, the question again is what price causes that demand. So we're going to have to use our formula for price. Remember our formula there that we derived is 35 minus x over 100. So 35 minus 1750 over 100. And that gives us a price of $17.50. So we should sell our tickets for that amount, and we'll get the maximum amount of revenue that we possibly can. So the main thing here is that our problems are pretty much exactly what we dealt with in the last section, where once we can actually set up a function, we are able to actually just go ahead and maximize it or minimize it the exact same way. Using our techniques of differentiation and finding those critical points, we can go ahead and maximize those functions. The main thing here is exactly how we set up those functions requires us to remember these particular concepts, these particular formulas. Now there is a little bit more to this section. We're going to go through a kind of a related topic, but I'm going to put that into its own video. So I'm going to end this one here, and I'll see you in that one.